So in this section, we turn to Chapter 2, and we'll be discussing dynamical systems. Why are we discussing dynamical systems? Well, we'd like to be able to build up our language in terms of sort of models that people oftentimes write to describe various kinds of systems before turning in more depth to likelihood-based methods and eventually kind of slightly more sophisticated Bayesian methods. So dynamical systems are systems typically that, as we said, kind of evolve in time. They do something. This could be time, and this would be sort of a time is equal to 0, and some arbitrary time t. And one thing that pops up with dynamical systems is the fact that the data, for example, at one point will depend on the data at the previous point. So this is the data at one point in time, for example, could depend on the data at the previous point in time. And the data at the subsequent point in time can depend on the data at all previous times, and so on and so forth. So in general, we can write something like this down. 1 to n minus 1. In modeling dynamical systems, it's often the case that the previous history of the system is not quite as revealing as, for example, the immediate history. So what I mean by that is that in order to be able to understand where I'm going next at time t, I may only be interested in where I was at some previous time, let's call it t minus 1, and it may somehow be less relevant where I came from, all of my previous history. So, in very many cases, what we find is that this here can be simplified as this. This simplification has a name, and it's called the Markov assumption. Now, it turns out that in classical mechanics, in quantum mechanics, across the areas of physics, and very many areas of chemistry, the Markov assumption is actually exact. So if I give you the immediate previous time point, that's all I need in order to predict, and a model, that's all I need in order to predict the subsequent point. So for example, if you were in physics and I have a harmonic oscillator force constant, and I give you its position and its momentum now, then you can predict the subsequent position and momentum. You don't need to have the entire history of what went on. Now, for classical mechanical systems, and again, quantum systems, the Schrödinger equation, and a whole bunch of different analogies or paradigms in chemistry and physics, the Markov assumption is not an assumption because basically it's exact. But for more complicated things, this could be an assumption. So for example, social dynamics or political dynamics or any kind of sort of more complicated, weather and so forth, or climate, things will depend on more of their previous history than just the immediate time point. And so it can be considered an assumption under those cases. So we'll be dealing with 4 dynamical paradigms. And within those 4 dynamical paradigms, we will be making the Markov assumption. So the first dynamical paradigm is discrete courses in discrete time. And I'll explain exactly what a course is. A course means basically that you're hopping between various things. So you're going from 1 cell to 2 cells to 4 cells. It's discrete. And this is happening at various jump points, let's say. At various sort of intervals. Now, the other case would be to consider continuous courses in continuous time. So that would be sort of the example of a trajectory that I gave earlier. Where you can go, the number of sort of states available to you is infinite. You can't just go, so for example, 1 cell to 2 cells to 3 cells. Maybe in this particular case you have a continuous number. So maybe you're looking at the evolution of a temperature in time. And time is continuous. It's not sort of at some regular interval. And why, by the way, would we be using regular intervals for time? Not because that's realistic or that's physically motivated. It isn't. Physics tells us that time is continuous. But because maybe my measurement apparatus measures things at various sort of discrete time intervals, and so it becomes natural for me to do my analysis within that paradigm in discrete time. And of course, I think you guys can imagine what the other two off diagonals are going to be. This is discrete courses, continuous time, and this is continuous courses in discrete time. Right, so maybe here continuous course, I could again have some kind of trajectory, but I'm only looking at it at various regular time intervals of measurement. Here instead, let's start off with this one. Here instead I have sort of discrete course. So maybe I'm hopping between one of two regions in space. So this is kind of region 1, this is kind of region 2. And it's happening at various sort of discrete intervals. And here instead, again, discrete courses. So I'm hopping between various courses, but this is not happening on a discrete grid. Here I can spend any time I want here, then any time I want here, any time I want here. In contrast, here I had to spend 3 units of time here, 2 units of time here, 2 units of time here, 2 there, and maybe 1, 2, 3, 4 here, right? So I spent a discrete amount of time visiting some discrete region of space. And here I'm spending a smooth, continuous amount of time visiting, in this case here, a discrete sort of state space. So hopefully these 4 paradigms make sense. We will start off, and I should say this one here is probably the most difficult and is dealt with very rarely. So we will start off with what is perhaps the easiest right now, which is kind of discrete courses before we move to continuous courses. And let me just introduce a couple of important topics, and I'm going to have time here, and I'm going to have states that I visit here. And I'm going to consider sort of the discrete course paradigm. When I have a discrete course, I say that I visit various states. So, for example, this could be one state, this could be another state, and this could be a third state. And I could be doing something like this, right? I could be going from, let's say, state 1. At some later time, I could be visiting state 2. And at some later time, I could be visiting state 3 before reverting back to state 1. Now, this path here I call a trajectory, which sort of makes sense. And in this case, I would say I have a trajectory in some discrete state space. Now, in this class, it's going to be very important to distinguish 2 different kinds of states. So we will talk about constitutive states, and then we will talk about passing states. And I have to sort of explain those in the context of this diagram here. So the constitutive states are the states to which I can go. So that's state 1, 2, and 3. And those states typically are given the variable sigma 1, sigma 2, sigma 3. Those are the different, let me just remove the word time here because it's interfering. Those are the 3 different states that I can visit. Passing states are a little bit different. Passing states are where I pass at a particular time. And those will be referred to as S1, S2, S3. Now let me explain that for a second. Here, I'm going to call this S1. And while I was passing through the state that I passed through was sigma 1. Next, this is my S2. The state that I passed to here is sigma 2. Now here is my next passing state. The state that I pass is sigma 3. Well, now something interesting happens. I go back here. My fourth passing state is not sigma 4 because sigma 4 doesn't exist. I only have 3 states. Now my passing state is sigma 1. My passing state is S4, and S4 is realized to sigma 1, my first constitutive states. So my constitutive states tell me the allowed state space through which my passing states can pass. Very simply. Why are we making such a big deal out of this? Because if we use the word state, state, state everywhere, it kind of starts sounding confusing. Our goal is not to learn constitutive states. When we start a problem, we know what our constitutive states are. Oftentimes what's unknown to us is what state we may be passing through at any given time. So the state space itself is typically known, but the passing states are not. So later on, we'll be doing more sophisticated examples where we'll be looking at, for example, signal versus time, and it may look something like this. And for that type of signal, we'll be asking, given that we know that we have 2 constitutive states, can you tell me what passing state I'm passing at, for example, every point in time? And we will be saying, yes, maybe here you are mostly in the second constitutive state. Later, you've transitioned to your first consecutive state. Then you've transitioned back to your second constitutive state. Then, oops, here we think that you passed through the first constitutive state again before coming back to the second constitutive state. So our goal, therefore, is to distinguish between the things that we want to learn versus the things that are given. And the things that are given is the constitutive states. The things that we want to learn are how are the individual passing states realized. So when we describe dynamical systems, and this is true for all 4 paradigms, there's a couple of things that we need to know. And the first one is, what are the system's states? So if I have a discrete state space, then my discrete states are sigma 1, sigma 2, sigma 3, and so forth. But maybe if I'm a Brownian particle diffusing in solution, I have an infinite number of constitutive states, and those states are my position, right? So those are the allowed states that that I can visit. So in describing dynamical systems, we first have to sort of specify what is the allowed state space. Then we have to ask, where does the system start? This is sometimes called the initialization rule. Finally, we can ask about how does the system evolve? So given where it started, how do we decide where it goes? That's the transition rule. How you transition from one state, whether it's in discrete space or continuous space. What are those rules? So for example, for a classical particle, the rule could be F equals ma. Given its positions and its velocities, you'd like to be able to, and the forces, you'd like to be able to propagate it in real space. And finally, there's a last one, which we won't focus on this chapter, but which will become absolutely critical for later chapters, which will be the assessment rule. The assessment rule, which is how are the states related to measurement. In other words, how are the data generated? And that's very important because I need to know sort of how my output is, and presumably probabilistically related with some kind of measurement error, how my output is related to what state I'm visiting at any given point in time. So, for example, I may be in this particular state, but when I carry out measurements at various points, I'm not going to get a perfect indication of what state I'm in, but I'm going to get some estimate. Maybe I'm going to fluctuate around this value. Here I may fall exactly on that sort of mean value, but then here I kind of have a large deviation again, and another deviation before sort of coming back closer. So maybe this is my constitutive state 1 and my constitutive state 2. And then eventually at later points I start transitioning to state 2. But if I connect the dots, in this particular region of time, up to, for example, this point here, I was in state sigma 1, and then afterwards I transition in state sigma 2. But if I look at the measurements themselves may be a little bit distorted because of measurement error, because there's an assessment rule. I don't see the states directly, I see kind of corrupted versions of them based on my experimental apparatus. So oftentimes we say that the states when we have measurement error, which is always, are hidden. Or sometimes we refer to them as being latent. Latent is just a fancy word for saying hidden. And oftentimes our job may be to learn what state we are in at any given point in time.